In our next set of examples, we will be looking at exponential functions that model growth and decay in applied problems, and that is all based off of this theorem. This theorem tells us that if we have a function that's differentiable, that is positive, and dy dt is equal to ky, then y equal to ce to the kt is a general solution for that differential equation. So what this really means here, this yellow box right here, what that's saying is that if the rate of change of y is proportional to y, that's what this means, the rate of change of y with respect to t, that's the derivative, is equal sign proportional to y, that's the k constant of proportionality multiplied by y, then this is our solution for y. Y is equal to ce to the kt. So let's put that into practice with an example. So in example 3, we have that the rate of change of y is proportional to y. That first sentence there means that the rate of change of y, which is dy dt, and I'm using t because I can see they're using t as an independent variable in here, is equal sign proportional to, I need a constant of proportionality, y. So I have dy dt is equal to ky. Just from that differential equation alone, Theorem 6.1 automatically tells us that the solution to this equation is y is equal to ce to the kt. We don't have to do any integrating. We don't have to separate variables. If we have a differential equation that looks like this, where the rate of change is proportional to y, then we automatically know that the general solution has this form. They tell us that when t is equal to 0, y is equal to 2, and that when t is equal to 2, y is equal to 4. And we're being asked to find the value of y when t is 3. So what we want is we want to know what is y of 3. So I want to know what do I get out of this function when I plug 3 in for t. But in order to do that, we need to find k and need to find c first. And to find c and k, we're going to use the two initial conditions that they gave us. So here they gave us an initial condition that when t is equal to 0, y is equal to 2. So I'm going to plug in 2 for y and 0 for t. Anything to the 0 power is equal to 1, so I automatically get from this that c is equal to 2. So we have c. I now know that c is equal to 2. Let's go on and find k. The second initial condition that they gave us is that when t is equal to 2, y is equal to 4. So I'm going to plug in 4y, and I'm going to plug in 2 for t. But remember that we already know that c is equal to 2. So I'm not going to write c, I'm going to put 2 for c. And then I have k, and I'm plugging in 2 for t. So I'm going to divide both sides of this equation by 2, which tells me that 2 is equal to e to the 2k. I'm trying to solve for k, so I'm going to need to use natural log on both sides, because natural log will cancel out the e and just leave me with 2k on the right side of the equation. And then to solve for k, I'll need to divide both sides by 2. So I get that k is equal to 1/2 natural log 2, or natural log 2 divided by 2, same thing. So now I can go back up here, and for k, I can put 1/2 natural log 2, and that is multiplied by 3. So this gives me approximately 5.657 for our answer when we plug that all into the calculator. Our next example begins by telling us that radioactive decay is measured in half-life and that the rate of decay is proportional to the amount present. So what that means then is that the rate of decay, if I were to call that dy dt, is proportional to the current amount present, the current value at y, that has the same setup as what we saw in theorem 6.1. So that tells us that y is equal to CE to the KT. They also go on to tell us that this is decaying, and so we definitely know that our value of k is going to be less than 0. So let's use this information in example 4. So we're dealing with radioactive decay, so we automatically know that our equation is going to have the form y is equal to CE to the KT. We're being asked how long will it take for 10 grams to decay to 1 gram. So we're starting with 10 grams and we want to know what is T, because how long will it take when y is equal to 1, when there is only 1 gram left. The 10 grams was the initial amount that we started with, and the initial amount is our C value. So that was given to us back up in theorem 6.1. Theorem 6.1 tells us that C is the initial value of y and k is the proportionality constant. So I know that my equation is 10e to the kt. What we do not have is we do not have k. And we will find k using this information here about the half-life. So what that means is that when t is equal to 24,100, half of the amount of plutonium has decayed. So we started with 10. Half of 10 would be equal to 5. So we only have 5 grams left after we have gone through 24,100 years. So this information about the half-life can be used almost like an initial condition, where we could plug this in and then we'll be able to solve for k. So I'm first going to divide both sides by 10, which will give me 1/2 is equal to e to the 24,100k. I'm trying to solve for k. I'm going to need to use natural log to cancel out the e. So I'll get natural log of 1/2 on the left side, and on the right side, when I plug the e to the 24,100k into natural log, the e and the natural log cancel each other out, and I'm only left with what we had in the exponent. Then to solve for k, I need to come in and divide both sides of this equation by 24,100. And that gives me that k is approximately, I'm going to use several decimal places here, negative 0. We have 4 zeros after the decimal place, and then 28761. And I'm doing that just so we don't end up with any rounding errors. So we get that the answer for our model y is equal to C we know is 10, that's the initial amount, e to the k, we just found an approximation for k, and k is multiplied by t. Remember that we were being asked how long will it take for 10 grams to decay to 1 gram. To figure that out, we need to plug in 1 for y, and then we want to solve for t. At this point, this is now a pre-calculus problem. We want to solve this exponential equation for t. I'm going to isolate the exponential by dividing both sides of the equation by 10. So I get that 1/10 is equal to e to the kt. I'm going to use natural log on both sides to cancel out the e. I'm only left with what was in the exponent on the right side of the equation. And then to solve for t, I'll need to divide by this decimal on both sides of this equation. So I get that t is equal to approximately 80,059 years when I put this fraction here into the calculator. In our next example, we have a population of fruit flies increasing according to the law of exponential growth. Because this is increasing according to the law of exponential growth, I know that the equation looks like y is equal to CE to the KT, and we also know that k is greater than 0. They give us some information. They tell us that there were 100 flies after the second day. That means that y is equal to 100 when t is equal to 2. So I plugged in 2 for t and y for 100. gives me that equation in blue. They also tell us that there's 300 flies after the 4th day. That tells me that when I plug in 4 for t, we get out 300 for y, which would give us this equation. We're being asked to approximate how many flies were there in the original population. So what we want to know what C is, because remember, the original amount is always the C value that you would get when t was equal to 0. So I'm going to take the first equation and I'm going to solve for C. And I'm going to do that by dividing both sides by e to the 2k. So I get that 100 over e to the 2k is equal to C. I'll rewrite that with a negative exponent as such. So I just took this e to the 2k that was in the denominator and wrote it with a negative exponent. So now that I have an expression for C, I'm going to take this expression for C and I'm going to substitute it into the second equation. So in the second equation we have 300 equals C. Instead of writing C, I'm going to write 100 e to the negative 2k, and that's still multiplied by e to the 4k. And the reason that I do that is because now this new equation only has k in it, and we'll be able to solve for k. We can combine these two terms here, e to the negative 2k and e to the 4k, by adding those exponents to get e to the 2k. And now I'm going to solve this equation for k. I'll start off and divide both sides by 100, which will leave me with 3 on the left-hand side. I'll need to use natural log. That will cancel out the e on the right side and just leave us with the 2k. And then we'll divide both sides by 2 to get that k is equal to 1/2 natural log 3. Now that we know what k is, we can go and plug that in to the expression that we had for C earlier, leaving us with C is equal to 100 e to the negative 2 multiplied by 1/2 natural log 3, which gives us that there were approximately 33 flies in the original population.